Hello guys, welcome back to CFD College. I'm Ashkan and this is the last tutorial of Fluid Mechanics 1. Not the last video. The last video of Fluid Mechanics 1 will be solving the last assignment F I think, which has 11 or 12 problems of fluid pipes, uh, chapter 8 of the book. But in this video, I'm going to solve tutorial 12, which has 3 problems regarding flow in pipes. I hope you've enjoyed this playlist, this series of videos. I tried to do my best in teaching you. I tried to show you fluid mechanics is not difficult, it's easy. You just need to follow some steps in order to solve different problems. And I hope, as I mentioned, I hope you like these videos. If so, please share these with your friends in the next semesters and let them let them learn this course. So let's jump to this tutorial. Tutorial 12. In this chapter 8, I mean, you have to solve flow inside pipes, whether we have pump, reservoirs, open tank, closed tanks, it doesn't matter. The focus is on flow inside the pipes. In previous chapters, we usually ignore the head loss, but in this chapter you learn how to calculate the head loss HL in the energy equation. It's equal to FL over D V square. This is V. V square over 2G. It's not difficult, but you have problem with friction factor. The main focus of this chapter is to show you how you can find this friction factor. This F friction factor is really important, not only in this course but also in your research, your future research, flow inside pipes, flow over different bodies, for example air force or anything. In any internal and external flow, friction factor is important. This chapter will show you how you should calculate this F in both laminar and turbulent flow. As you know, in laminar flow it's equal to Reynolds over 64 over Reynolds number, but in turbulent flow, so this is for laminar flow, this is for turbulent flow, you have some equations. They are not explicit, they are implicit equations. It's hard to work with them, it's difficult to use them. You need you can't do it on paper, you need advanced calculator. The second way is to use Moody Chart. So it's important for you to learn how to work with this Moody Chart. So first of all, let's have a look at this Moody Chart. I think I have it here. Okay, yes, this is the Moody diagram, Moody Chart. Let me screen right. It's okay, I think it's activated right now. Here you see that we have with the red color, we have friction factor, on the horizontal axis we have Reynolds number, and on the right vertical axis we have pipe roughness, epsilon over d. We have different lines here. This line, laminar flow, it shows us the laminar flow expression. As you can see, 64 over Reynolds, it's a linear. And these are lines that you can use in turbulent flow, based on Reynolds number and dimensionless roughness, epsilon over d. Epsilon is the roughness height, maybe, and d is the diameter of the tube. You should find epsilon over d and Reynolds number on this chart, and then, for example, for this point you can read friction factor. You can use either this line or any line, depends on the Reynolds number and relative pipe roughness. But here we have this line. The lowest line is for smooth pipe. For example, if you have a plastic pipe like what we had in previous tutorial, I think a plastic pipe is a smooth pipe, so you don't have a roughness in smooth. You don't have roughness in smooth pipe. Then, so if you had smooth pipe, you don't need to consider epsilon over d because it's 0, and it means that you have to look only at only this line. So you only need Reynolds number, and then you can find friction factor. Here in this specific chart, which is available on Wikipedia, you can see the roughness for different materials. As you can see, the roughness depends on the material of the pipe. So having said that, we can go back to our problems. The first problem number 68. Let me increase it a bit. Problem number 68. In 1/2" diameter, half-inch diameter house shown in the figure below can withstand a maximum pressure of 200 psi. So this pipe, here we have a pipe, a pump, and this is the water tank. The diameter of the pipe is 0.5 inches. The maximum pressure in the system should be 200 psi, the maximum pressure that the system can withstand. Determine the maximum length L, the length of the tube allowed if the friction factor is 0.0. In this problem, as you can see, the main issue is done, and we know the friction factor, because if we don't have that, you will see in future problems, in next problems and future video, the assignment, it's difficult because you have to do trial and error test, because most of the times we don't have a velocity or diameter, so we don't have Reynolds number. Results in a confusion, because we can't measure f, can't find f. So in that case, you have to assume a value for f, solve the problem, find velocity or diameter, I don't know, the unknown parameter. Then you should calculate Reynolds number and recalculate f using this diagram, and then solve the problem again and again and again. But mostly 3 times is okay in these types of problems. But here in this problem, we know friction factor and also the flow rate Q is equal to 0.01 CFS, cubic feet per second. Neglect the minor losses. Minor losses mean when the flow enters this pipe, or we have this nozzle here at the tip of the pipe. So here we have a minor loss. Remember that HL is actually the head loss is a major loss, not minor loss. Okay, now we should solve the problem. So we have the flow rate, we have the diameter, so we can calculate the velocity. But first, let's think about the location of the maximum pressure. As you know, in all these pipes, we have a friction. And due to friction, we have pressure loss. So as we move along this pipe, pressure decreases. So it means that the maximum pressure is not happening here or here or here. After the pump, we should have the maximum pressure. As you know, pump adds energy to the fluid. Increase the pressure actually. You know it. So the maximum pressure in the system is at this location, just after the pump. So the maximum pressure is here. This is the first important point. And here the outlet should be the second key point, because we know the pressure of this point, and actually we have the velocity. We can calculate it because we have the flow rate and the diameter of the nozzle. In problems in this chapter, mostly you have to use energy equation because we have a fluid flow. So as I mentioned in previous videos, previous chapters, for energy equation, we have to firstly find our key points. So now we have our key points, point 1 and point 2. Now we can use energy equation, P1 over gamma, and you have to always follow the flow. Plus V1 square over 2G plus Z1. There is a pump in the system, but it's not between point 1 and point 2. So we shouldn't add this head pump because it is not between point 1 and point 2, although it's in the system. But we shouldn't consider it. So it equals P2 over gamma plus V2 square over 2G plus Z2 plus HL. That's the reason that you have to follow the flow, because HL, the head loss, should be on the right hand side of the energy equation. And you know that this, if HL equals F L over D diameter, V square over 2G. Now it's time to think about what we have and what we know. So we know that P1 is the maximum pressure in the system. So P1 is 200 psi. We know that Z1 is, if Z1 is 0, if we place the axis here, then Z2 equals 10 feet. What else? We know that at the exit we have atmospheric pressure, so the gauge pressure of the exit is 0, P2 is 0. And we also know that velocity, we have three different velocities: v1, v2, and v. v2 is the velocity at the exit. Be careful that we have a nozzle at the tip of the at the end of the pipe, and the water flows through this nozzle. So the exit diameter is 0.3 inches. So if you want to calculate V2, which is Q over A2, you have Q 0.01 cubic feet per second. A2 is pi over 4 times diameter of this nozzle, the tip of the nozzle, 0.3 over 12. Don't forget that we need feet square, which is equal to 20.4 feet per second. But for V1, we should use the cross-sectional area of the pipe over A1, so 0.01 cubic feet per second over pi over 4, 0.5 over 12 feet square, which brings us 7.33 feet per second. What about this velocity? The velocity that we have in head loss formula, HL, is always the velocity that we have inside the tube, the pipe. So V equals V1, not V2. Careful about that. The velocity inside the pipe equals V1, not V2. V2 is the velocity due to the nozzle. Okay, now I think we have everything, so we can solve the problem. 200 psi, pounds per inch square, times 144 inches square over feet square over gamma, 62.4 pounds per cubic feet, plus V1 square, feet per second square, over 2g, 2 times 32.2 feet per second square, plus Z1, which is 0, equals P2 over gamma is 0, V2 square, 20.4 feet per second square over 2 times 32.2 feet per second square, plus Z2, 10 feet, plus F L, we want to find it, over diameter, 0.5 over 12 feet, times V2, V1, over 2 times 32.2 feet per second square. And from this you can find L. L equals 1012 feet. It was easy, but now let's solve the second problem. It's really good problem because it is a combination of control volume and flowing pipes. Problem number 87. Water flows through the pipe shown in the figure below. Determine the net tension in the bolts. If minor losses are neglected, minor losses, not major loss, and the wheels on which the pipe rests are frictionless. Okay, so these are not important information because we know that we shouldn't consider them. So this is the pipe. We have a reservoir here. Water flows through this pipe. The diameter is 80 millimeters. It is fixed, so the velocity in the pipe is fixed. Here are the bolts. So we want to find the tension. Tension is a force. When you want to calculate the force, you have to use control volume. So the first step, draw the control volume. This is our control volume. We have control surface here, which is the outlet, CS2. Here we have a sort of inlet, CS3. So this is the control volume. Let me draw it here. CS2, CS3. Here we have outflow. This is V2. We have inflow here, V3. And here we have atmosphere at the exit, but here we are at the middle of the pipe, so don't forget to consider the pressure force, P3A3, and the pressure force is always parallel to the control surface towards the control volume. And we have this force that we want to find, FB. So this is the sketch of the control volume, the forces, and the velocity. The next step is to define x and y axis, x and y. And now we can solve it. So if you remember, the summation of forces in x direction equals the change of momentum inside the control volume, which is 0 because we are working at steady state, plus the exchange of momentum through control surface is Vx rho V dot n dA. So we have two forces, P3 A3 minus FB. It equals, we have two control surfaces over control surface 2. V2 is horizontal, so V2 rho V dot n, we have outlet, so it's positive V2 dA plus over control surface 3. V3 is in the direction of x-axis, so V3 rho, but here we have inlet, so we should use this negative sign, minus V3 dA. That's easy. So P3 A3 minus FB equals rho V2 square A2 minus rho V3 square A3. Okay. As you know, since diameter is fixed, so D2 equals D3. And we know that flow rate is fixed. Actually, Q2 equals Q3. It's the conservation of mass. From these, we can find that V3 equals V2. So these terms are equal. V2 equals V3, A2 equals A3. So it's equal to 0. So FB equals P3 A3. We know A3, but we don't have pressure at point 3. So if we find it, we can solve the problem. Okay, so here we have point 3, point 2, and it's obvious that at this free surface we have the first key point. Okay, now we use the energy equation between point 1 and point 2 to find the friction first. After having the friction, we can use energy equation between point 1 and 3 or 2 and 3 to find pressure at point 3. So energy equation between point 1 and 2, P1 over gamma plus V1 square over 2G plus Z1 equals P2 over gamma plus V2 square over 2G plus Z2 plus HL, which is FL over D V square over 2G. But what do we know? Both point 1 and point 2 have atmospheric pressure, so P1 equals P2 equals 0. And if Z2 is 0, Z1 is 3. Meters. And what else? Point 1 is a free surface, so V1 equals 0. And the velocity inside the pipe equals V2 equals V3. So this V equals V2 or V3. It doesn't matter because V2 and V3 are equal. So this term and this term and this term and this one, they are all gone. So what remains is Z1 equals V2 square over 2G. If we factor out 1 plus F L over D. Yes. So 3 meters equals 1 plus F times L, which is 10 plus 20, 30 meters over diameter 80 millimeters, 0.08 meters times V2 square over 2G, 9.81 meters per square second. So from this you can find that 58.9 equals 1 plus 375 F times V2 square. This is the equation that we can find from energy equation. So as you can see, we don't have F and velocity, so we can't solve this. What else do we know? We know that Reynolds number, to find F, we need Reynolds number equals V D over nu. So we don't have V, velocity, we have the diameter and the kinematic viscosity of the water. 1.12 10 to power minus 6 meters square per second. So Reynolds number equals 7.14 10 to the power 4 V2. As you can see, we have two equations. So since we don't have Reynolds number, we can't find F. Since we don't have F, we can find velocity. So we have to do trial and error. First, this is galvanized iron. So from table 8.1 in the exam, this should be given to you, but here from table 8.1, the first table of the chapter 8, we can see for galvanized iron, epsilon equals the roughness equals 0.15 millimeters. So epsilon over d, we have the diameter 0.15 millimeters over 80 millimeters equals 0.00188. So this is the dimensionless roughness. So we have to do trial and error. So first we assume f equals 0.02. Always start from this assumption. So if we have f, let's call this equation 1 and this one equation 2. From equation 1, you can find velocity, 2.63 meters per second. From equation 2, by having velocity, you can find Reynolds number, equals 1.88 10 to power 5. Now, by having the Reynolds number, 1.88 10 to power 5, and epsilon over d, 0.00188, you can find F, friction factor from Moody diagram, 0.245. So this is from Moody diagram. Now by this new F, you have to do the math again. So F is this one. From equation 1, you can find velocity equals 2.4 meters per second. Then by equation 2, you can find Reynolds number 1.72 10 to 5. And now by this Reynolds number and epsilon over d equals 0.00188. Then again, if you go to Moody Chart, you can find F, which is pretty similar, 0.0245. So this results in velocity equals 2.4 meters per second from equation 1. So now you have both friction and velocity. Now you can use energy equation between point 3 and 2 to solve the energy equation and find pressure at point 3. But remember, this is the direction, the flow direction, so we should start from point 3. P3 over gamma plus V3 square over 2G plus Z3 equals P2 over gamma plus V2 square over 2G plus Z2 plus FL over D V square over 2G. Now we know that we want to find P3. We know that V2 equals V3 equals V. So here the velocity between point 2 and 3 equals V2 or V3. We know pressure at point 2 is 0. What else do we know? We know that Z2 equals Z3 because the pipe is horizontal. So these terms are cancelled. This one is 0 and these are cancelled too. So we only have these two terms. P3 over gamma equals FL over D V square over 2G, or P3 equals FL over D rho V square over 2. So P3 equals F 0.0245. It's dimensionless. L between point 3 and point 2. We just this 20 meters. Over D 0.0245. 0.08 meters. Rho of water, we don't need this, 999 kilograms per cubic meters. Velocity 2.4 meters per second square and divided by 2. So from this you can find the pressure at point 3 equals 1.76 10 to 4 Newton per square meter, and having that you can find FB. P3 A3 equals 1.76 10 to 4 Newton per square meter times velocity pi times area times pi over 4 and the diameter to the power 2. So FB equals 88.5 Newton. This is a very difficult problem. I agree with you, but it's the typical problem that you should solve in after passing fluid 1. The next question, the last one. Problem number 102. Water is pumped between two large open reservoirs. So this is the first one. Here is the pipe. This is the pump. And this is the second reservoir. Through 1.5 kilometer of smooth pipe. So this is the smooth pipe. It means epsilon is 0. The length of this pipe equals 1.5 kilometers. The water surfaces in the two reservoirs are at the same elevation. So here are the water surfaces. When the pump adds 200 kilowatt, so we know the net power of the pump to 200, I said 20 kilowatts. To the water, the flow rate equals 1 cubic meters per second. If the minor losses are negligible, determine the pipe diameter. Here again, the minor losses are negligible, not the major loss. Determine the pipe diameter. So we don't have this diameter. It's easy for you because the first step is to identify the key points, and it's easy. We have two free surfaces. These are our key points. Let's write down the energy equation between these two, and for example, assume that the flow goes from left to right, flows from left to right. So P1 over gamma plus V1 square over 2G plus Z1 equals P2 over gamma plus V2 square over 2G plus Z2 plus FL over D V square over 2G. What do we know? P1 equals P2 equals 0 because both are free surfaces and atmospheric pressure. So P1 equals P2 equals 0. At these free surfaces, velocities are also 0. So V1 equals V2 equals 0. That's why I never put the subscript for this velocity. Leave it and then think about it. And also Z1 equals Z2 because of the same elevation we have in these reservoirs. So all terms, what do we have here? Oh, sorry, I forgot HP plus HP. We have a pump in between. So all of these terms are zeros except of these two. HP equals FL over D V square over 2G. This velocity is the velocity we have in the pipe. So we have to use the flow rate to calculate it, and we have to use this net power of the pump to calculate HP. As you know, HP, the head pump equals W dot, the net power over gamma times Q. We have all of them. W dot is 220 10 to 3 Newton meter per second. Gamma of water 9.80 10 to 3 Newton per cubic meters times flow rate 1 cubic meters per second. So from this you can find HP 2.04 meters. And velocity equals Q over A, so it equals 1 cubic meters per second over pi over 4 d square. So velocity equals 1.273 d square meters per second. So having velocity, we can calculate HL, which is F, we don't have it. Length of the tube, L, 1500 meters, over D, we don't have it, times velocity, 1.273 over D square, V square, don't forget that, over 2G times 9.81, this is 2 meters per second square. It equals 123.9 F over D to power 5. So we have this 2.04 equals 123.9 F over D5. So F equals, or D, let's say D, it's easier. No, F or D. D is easier. We should find D. It's not easier, but we have to. 2.27 F to power 1 over 5. This is one equation that we have. The second one is Reynolds number equals rho V D over mu. Rho is 999 kilogram per cubic meters. Velocity 1.273 over d square times d over mu, 1.12 10 to minus 3 Newton second per square meter. So Reynolds number equals 1.14 10 to 6 over d. So this is equation 1. Reynolds number is equation 2, like what we did. And remember that here we have a smooth pipe, so epsilon is 0, so we have to use the lowest line in the Moody diagram. Just like what we did in previous example, we should assume F equals 0.02. Then from equation 1, you can find diameter 1.04 meters. And from equation 2, Reynolds number equals 1.1 10 to 6. Now at this Reynolds number and this smooth pipeline on the Moody diagram, you can find new friction factor 0.0115. Again, from equation 1, diameter can be found at 0.931 meters. So from equation 2, Reynolds number is 1.22 10 to power 4. And now with this Reynolds number and the smooth pipe, from the Moody chart, you can find F 0.0113. So from equation 1, diameter is 0.927 meters. From equation 2, Reynolds number is 1.23 10 to power 4, and from Moody chart you can find F, which is 0.0115. So actually we have solved the problem. The diameter, the final diameter equals 0.927 meters. We wanted to find the diameter of the pipe. So that's it. This is the end of this video. We solved 3 problems. I hope you've enjoyed it. If so, please share these videos with your friends. I have many videos about CFD, numerical simulations, drawing different charts in different software. You can enjoy them too, and you can be with us in the future. Thank you for watching this video. I hope you get a good grade in this course. Take care of yourselves and bye bye.